Hi, my name is Liang Babang Dangasi, and in this video I'm going to discuss the Chapter 5 Gases, Section 516 titled The Kinetic Molecular Theory of Gases, and the Section 517 The Effusion and Diffusion. What is Kinetic Molecular Theory of Gases? Kinetic molecular theory explains the macroscopic properties of gases and can be used to understand and explain the gas laws. It states that gas particles are in constant motion and exhibit perfectly elastic collisions. It can be used to explain both Charles and Boyle's law. So what does kinetic molecular theory do? So Kinetic molecular theory, though, explains why gases behave as they do. So, what type of particle does kinetic molecular theory deal with? It deals with ideal gas particles. So far we have considered what happens but not why. In science, what always comes before why. So in simplest terms, a law predicts what will happen while a theory proposes why. A theory will never go into a law, though the development of one often triggers progress on the others. So, postulate of the kinetic molecular theory. So, what is postulate? Postulate, it is all matter, consists of indivisible particles called atoms. Atoms of the same element are similar in shape and mass but differ from the atoms of other elements. Atoms cannot be created nor destroyed. So as you can see in the picture, that is the example of postulate of the kinetic molecular theory. So at the left side sample, which is the container, and this is the particles of the inside in the container. And the next sample is the balloon, and this is the particle of the inside in the balloon. So number 1, the particles are so small compared with the distances between them that the volume of the individual particles can be assumed to negligible or zero. So gas particles are hard spheres with no internal structure. The volume of the individual particles is negligible in comparison to the average distance between particles. So gases also are tiny molecules in mostly empty space because of the compressibility of gases. The particles that compose a gas are so small compared to the distances between them that the volume of the individual particles can be assumed to be negligible, zero. So number 2, the particles are in constant motion. The collision of the particles with the walls of the container are the cause of the pressure exerted by the gas. So the collision of the gas particles with each other and the walls of the container are elastic, resulting in no loss of energy, only change in direction. So the molecules collide classically with container walls and one another because of the gas's exerted pressure that doesn't diminish over time. So when we see elastic collision, it is an encounter between two bodies in which the total kinetic energy of the two bodies remains the same. In an ideal perfectly elastic collision, there is no net conversion of kinetic energy into other forms such as heat, noise, or potential energy. The molecules move in constant rapid, random, straight-line motion. Gas moves rapidly. So the motion of the gas particles is completely random so that statistically all directions are equally likely. So number 3, the particles are assumed to exert no forces on each other. They are assumed neither to attract nor to repel each other. So the gas particles neither attract or repel one another, so they possess no potential energy. Because there are no attractive forces between molecules, gases do not clump. So number 4, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. So the collective motion of individual gas particles creates a statistical distribution of velocities in the sample. The average velocity of the gas particles increases with temperature and decreases with the mass of particles. The average kinetic energy of the molecules is proportional to the Kelvin temperature of the sample. According to Charles' law, Newton's first law of motion, law of inertia, object at rest tends to stay at rest and object in motion tends to stay in motion at constant velocity unless object is acted upon by an unbalanced external force. So that's all for the postulates of the kinetic molecular theory. So next is concept check. You are holding two balloons of the same volume. One contains helium and one contains hydrogen. Complete each of the following statements with different or the same and be prepared to justify your answer. So first, the pressure of the gas in the two balloons are the same. The temperature of the gas in two balloons are the same also. The number of moles of the gas in the two balloons are the same as well. The densities of the gas in the two balloons are different. So, to justify my answer, why pressure, temperature, and number of moles are the same but the densities of the gas in the two balloons are different. So, according to Avogadro's principle, the volume and moles of the gas are directly proportional if the temperature and pressure are constant. So, according to Avogadro's law, equal volume of all gases contains equal number of molecules at the same temperature and pressure. Ideal gas is an imaginary gas which contains non-interacting particles and obeys gas law at any conditions. The collision of ideal gas particles are purely elastic. Hence, there is no attraction or repulsion. Volume of this particle are negligible. Ideal gases won't condensate into liquids at lower temperatures, at low temperature and high pressure. Real gases behave like ideal gases and it is known as perfect gases. So, note that if either temperature or pressure are varying, both are varying, the number of molecule will not be the same for gases with equal volume. It does not depend upon the properties of the gas. They will behave like the same gases even if it is helium and hydrogen gas because they are treated in the same condition. It's either a constant pressure, constant volume, and constant temperature. So next is concept check, sketch a graph. So first is pressure versus volume at constant temperature and moles. So this is the graph of the pressure versus volume. The graph states that temperature and moles are constant. This means that we are dealing with Boyle's law, which states that pressure is inversely proportional to volume. Inversely proportional means that the pressure increases as volume decreases and vice versa. So, volume versus temperature at 0 degrees Celsius at constant pressure and moles. So, this is the sketch of volume versus temperature at degrees Celsius at constant pressure and moles. So, volume and temperature. So, the graph states that the volume of a gas is directly proportional to its temperature when pressure is constant. The ratio of the volume to temperature is constant when pressure is constant. This relationship is known as Charles' law or Green-Lassax's law. So next is the third sketch graph is volume versus temperature Kelvin at constant pressure and moles. So this is the graph of volume versus temperature. the graph states that the relationship between volume and temperature, if the pressure and amount of gas are held constant. If the Kelvin temperature of a gas is increased, the volume of the gas increases, and if the Kelvin temperature of a gas is decreased, the volume of the gas decreases also. This means that the volume of a gas is directly proportional to its Kelvin temperature. So next is the fourth sketch graph, volume versus moles at constant temperature and pressure. So this is the graph of volume versus moles. This graph states that at constant temperature and pressure, the volume of a gas is directly proportional to the number of moles of gas. So, next is concept check. Volume is equal to volume. Ne is equal to argon. Which of the following best represent the mass ratio of NEER in the balloon? So, you are holding two balloons of equal volume. One contains argon and the other contains neon. What would be the approximate mass ratio between argon and neon in the two balloons? So, if you have balloons that are equal volume and you're assuming that there is equal pressure around them and equal temperature, that would mean your moles of argon are equal share moles of neon. So, Ne and Er it is going to Ne, so the mass ratio between the two would just be molar mass of argon over the molecular weight of neon. So the mass ratio of neon and argon in the balloons is ratio 1 to 1. Next is concept check. You have a sample of nitrogen gas in a container fitted with a piston that maintains a pressure of 6.00 atm or atmosphere. Initially, the gas is at 45 degrees Celsius in a volume of 6.00 liter. So, you then cool the gas sample. So, which best explain the final result that occurs once the gas sample has cooled? So, A. The pressure of the gas increases. B. The volume of the gas increases. C. The pressure of the gas decreases. D. The volume of the gas decreases. E. Both volume and pressure change. So, the best answer that explain the final result is the volume of the gas decreases, which is letter D. So, next concept check. The gas sample is then cooled to a temperature of 15 degrees Celsius. Solve for the new condition. Hence, a movable piston keeps the pressure constant overall. So, what condition will change? So, this 5.43 liter is the new condition of the gas sample. So, to get this new condition of a gas sample, we're going to use Charles law equation. So, next is, we have the given of volume 1 is equal to 6.00 liter. Volume 2 is the unknown. So, we're going to solve this to get this volume 2. Temperature 1 is equal to 45 degrees Celsius and temperature 2 is equal to 15 degrees Celsius and Kelvin is equal to 273. So, to get this 5.43 liter, we're going to solve this equation. Volume 1 over temperature 1 is equal to volume 2 over temperature 2. So, our volume 1 is 6.00 liter over 45 degree, which is the first temperature, plus 273, the given Kelvin, is equal to volume 2 over 15 degrees Celsius, which is the temperature 2 plus 273, the given Kelvin. So, volume 2 is equal to 43 liters. So we're going to cross multiply to get this 5.43 liter. So V2 is equal, multiply by 45 plus 273. 45 plus 273 is equal to 318. So 6.00 liter multiply by 15 plus 273. 15 plus 273 is equal to 288. So we're going to divide the 318 and the equal of 6.00 and 15 plus 273, and we get this answer, which is volume 2 is equal to 5.43 liter. So next is root mean square velocity. So this is the equation of the final units, meter per second squared. So this is V. V stands for meter per second squared. R is for root. M for mean. S for square. Is equal to square root of 3 RT M. So R means the molar gas constant. T is the temperature in Kelvin. And M is the molar mass of the in kilogram per mole. So R, the given, is equal to 8.3145 G per over K times mole. So G stands for joule and is equal to kilogram times meter squared per second squared. So T is equal to temperature of gas in Kelvin. M is mass of a mole of gas in kilogram. So the final units are in meter per second. So that's all for the discussion of the kinetic molecular theory of gases. So we're going to discuss the second topic, which is the effusion and diffusion in section 5.7. So diffusion, the mixing of gases. Diffusion is the movement of a substance from an area of high concentration to an area of lower concentration. So the diffusion occurs in liquid and gases when their particles collide randomly and spread out. So diffusion is an important process for living things. It is how substances move in and out of cells. So this is the example of effusion and diffusion. So effusion describes the passage of a gas through a tiny orifice into a evacuated chamber. So effusion describes the passage of a gas through a tiny orifice into an evacuated chamber. Next is rate of effusion, measures the spread at which the gas is transferred into the chamber. So rate of effusion measures the speed at which the gas is transferred into the chamber. The rate of effusion of a gas is inversely proportional to the square root of the molecular weight of the gas. The lighter the gas is, the faster it will diffuse, and the heavier a gas is, the slower it will effuse. So we're going to discuss the sample of effusion and diffusion. So this is the this left side, which is the lower concentration, because there is a lot of particles here, and then the right side is the high concentration, because the smallest particles, the particles we're going to transfer in the higher concentration through the pinhole. So this is what we call the effusion. Pinhole is the effusion of the chamber. So next is the Graham's law of effusion. Rate of effusion for gas 1 over rate of effusion for gas 2 is equal to square root of molar mass sub 2 over square root of molar mass sub 1. Molar mass sub 1 and molar mass sub 2 represent the molar masses of the gases. So that's all for effusion and diffusion. Thank you and God bless.